Okay, let us see how we handle this example. In the previous, I've been seeing how we get the forces. Now let us see how we get the angles. So now, find alpha and theta in the following if the string is in equilibrium. So here I'm not going to use Lami because we have three forces and the string is what? In equilibrium. So if I'm starting with alpha, is that alpha? It has this force opposite it, and then we have a complete set. So there I'm going to now first of all the complete set. I have the force up over the opposite angle of the force. So you see the opposite angle of the force is sine 120 degrees to be equal to 2. Now here I have my alpha, the angle is 10, the force is 10 over sine alpha. So if I cross multiply like this, I'll be having now sine alpha equaling to 10 sine 120 the whole over 15. And so my alpha from here, it would be sine inverse of the whole of this, which is 10, now sine 120 the whole over 15. And then I come and I get my alpha as so the whole of this. So there we are having so this will be 35.26 degrees. And I think you can easily get this theta here. Okay, let us turn to this. A particle mass 30 kilograms is attached to the lower end of an inaccessible string. That means that that string is not elastic. The upper end of the string is fixed to the ceiling of the roof. A horizontal force of 22 newtons and an upward force of 4.9 kilograms and newtons act upon the particle, making it be in equilibrium, the string making an angle alpha with the particle. Okay. So let us first consider our string. This is the ceiling. Again, that's that one's part is going to be at the ceiling here. Now, because there is a force acting, now first of all, this is what would have been with if there was no force. So that would what we'd be having. But because there is a force that is pulling this away, then our string is at an angle there. And then they are telling us that this angle is alpha. It's making an angle alpha with the particle. So now this is going to be the particle which is 3 kilograms. Of course, from there, we expect that this is going to act upon it, which is going to be 3 kilograms. Now, there is a force which is pulling this particle, and this force is 22 newtons because it is the one which is acting horizontally. And also have a force on this same particle which is acting vertically to that. And so this is going to be 4.9 newtons. Now, it's that this one will be alternating. So this angle here is going to be the same as this angle here, alpha. And because so we are going to expect some tension in that string there. Now, if we are to resolve this string here, the tension of this string, hope you can see, I can resolve it like this, then like this. So, you can resolve it up, then we come to this like this. It's up to us. So, we can now resolve this force like this, but it's not our force here, so I can say this, then like this. So, or we can say the force which we are going to be, this force is going to act upwards. Or I can do this. Then this one is going to be, I'm going to have a second force here, which I'm going to say. Now, this is going to be T, because this is an adjustment, so this is going to be T. Then cos alpha, and this is going to be, you see from this, it's going to be now T sine alpha. Now, if this body is in equilibrium, it means that now the upward forces are equal and then horizontal forces are also equal. So if I turn to the upward forces, upward forces. What am I having upwards? First of all, upwards, I have those which are going up. I have 4.9, you see in that direction, then plus t cos alpha, it will be equal to 3g. Because the body is in equilibrium, it means that the upward forces are equal, or the acceleration is 0 if the body is in equilibrium. So if you want that, you can easily solve that idea. So from here, I think you can see my t cos alpha is going to be 3, then this one is going to be 9.8, then minus 4.9. And so my t cos alpha is going to be, if you simplify that, this one is going to give us 24.5, and I call this equation 1. Now, you can let me see if I have this. Now I can say horizontal forces. Horizontal forces. Remember, Newton said is equal to MA. You can also use it here, but our A is equal to 0 because body is in equilibrium. Okay, so now my forces act in that direction. I have decided I'm going to be having 22, then minus, then this one which is opposing, t sine alpha. Now it's going to be equal to the mass, which is going to be 3, then times that acceleration which is 0. So that now my t sine alpha is going to be equal to 2. Now 22, and I call this an equation 2. So now I think you can see that you can easily solve this. If I say 2 divided by 1, so I have t sine alpha equal to 22, then divide by t cos alpha, then inside I'll be having 24.5. And you see this 2 will go, so we shall be having time alpha equaling to 22 over 24.5, and so my alpha will be here I'm getting 41.92 degrees. And if we have alpha, we can every come and we get our t from there. From here, so our t cos alpha is equal to 24.5 from which equation? From 1. Our t will be 24.5, the whole over cos of 41.92. And so our t here is going to be divided by cos of, and here I'm getting 32.9266 newtons. Now, how could we, I think we could see, if now we just add this tension, the vertical force, and then this, for the body to be in equilibrium, you can also apply it that way. I think, but I thought when I was doing this was a cheaper method to handle it. So that's it, members. I wish you well. So that's how we handle that. We are going to see more examples there.